In the last video, we have seen that if we can write the augmented matrix of a system in a nice form, then we can solve the system easily using the method of backward substitution. Such a matrix is said to be in row-echelon form, and its definition is given as follows. There are three conditions that a matrix needs to satisfy in order to be in row-echelon form. The first one is that any zero rows of the matrix have to be at the bottom, and by zero rows I mean rows consisting of only zeros. The second condition is that the first non-zero entry in each non-zero row is 1, which is called the leading one of that row. The third condition is that each leading one is to the right of the leading ones in the rows above it. So a matrix in row-echelon form would look something like this, where some region in the bottom left corner are all zeros, and the first non-zero numbers in each row must be a 1, and they appear in a staircase fashion. As I said before, if the augmented matrix of a system is written in row-echelon form, then we can do backward substitution directly to solve the system. Let's try to determine whether the following matrices are in row-echelon form. The first matrix that we have is this. This matrix is in row-echelon form because the first non-zero entries in each row is a 1, and also the leading one of the second row lies in the third column, which is to the right of the leading one in the first row, which is in the second column. The second matrix is this. We observe that the first non-zero entry in the second row is in the first column, which is to the left but not right of the first non-zero entry in the first row, which is in the second column. So the matrix is not in row-echelon form. The third matrix that we have is this. Similar to the second matrix, the first non-zero entry in the second row is in the second column, which is at the same column but not to the right of the first non-zero entry in the first row. Hence, the matrix is not in row-echelon form. The fourth matrix is this. We observe that there is a zero row of the matrix, and it lies at the bottom of the matrix. Moreover, the first non-zero entry in the second row lies in the third column, which is to the right of the first non-zero entry in the first row, which is in the first column. So, the matrix is in row-echelon form. Let's consider one more matrix. We observe that there is a zero row in the matrix, and it lies in the first row of the matrix, but not at the bottom. Hence, even though the leading one in the third row lies to the right of the leading one in the second row, the matrix is not in row-echelon form. Let's look at an example of solving a system of linear equations with an augmented matrix in row-echelon form. We observe that there is a zero row in the matrix, which we will ignore because it only states that 0 equals 0. So we start from the second row, which means that x2 plus x3 equals 1. Here we will set x3 equals some number, say a, and then we can express x2 in terms of a. Notice that we can also express x1 in terms of a by substituting x2 and x3 in the first row. Now the second row is x2 plus a equals 1, so x2 equals 1 minus a. From the first row, we have that x1 minus x2 plus 3x3 equals 0, which means that x1 equals x2 minus 3x3, so it equals 1 minus a minus 3a, so it is equal to 1 minus 4a. Now we have the general solution, which is 1 minus 4a, comma 1 minus a, comma a, where a is any real number. Notice that there are infinitely many solutions to the system, because for each a we have a different solution, and since a is a real number, there are infinitely many possible values of a, and hence infinitely many solutions. Here let's introduce some terminologies. x3 is called a free variable, which means that we are free to assign an arbitrary value to this variable, and we have assigned a in this case. A is also called a parameter, which means that its value can change, which will also change the solution. x1 and x2 are called leading variables, which means that they have a leading entry in the augmented matrix of the system. Indeed, The augmented matrix has a leading 1 in the first column and the second column, which correspond to x1 and x2 respectively. Let's look at one more example where the augmented matrix has the same number of equations but more variables. Again, we start from the last row, which means that x5 plus x6 equals 0. So we set x6 equals a to get x5 plus a equals 0, which means that x5 equals negative a. We substitute x5 equals negative a into the second row, which means that x4 minus x5 equals 3. So x4 equals 3 plus x5, which equals 3 minus a. Now we look at the first row, which states that x1 plus x2 plus x3 plus 3x4 plus 2x5 plus 4x6 equals 0. We already know x4, x5, and x6 in terms of a, but we have yet to find the values of x1, x2, and x3. We see that we have to assign 2 more parameters to x2 and x3, and after doing so, we can express x1 in terms of the parameters already defined. So we set x2 equals b and x3 equals c to get x1 plus b plus c plus 3 times 3 minus a plus 2 times negative a plus 4a equals 0. So x1 equals a minus b minus c minus 9. Thus, the general solution is a minus b minus c minus 9, comma, b, comma c, comma 3 minus a, comma negative a, comma a, where a, b, and c are all real numbers. Using the terminology in the last example, the 3 variables are x2, x3, and x6, and the leading variables are x1, x4, and x5. Bear in mind that the leading variables correspond to leading ones in the row-echelon form of the augmented matrix, and indeed, the leading ones in the augmented matrix are in columns 1, 4, and 5. So indeed, x1, x4, and x5 are the leading variables. Let's end this video with a theorem which states that every matrix A can be reduced to row-echelon form using elementary row operations. First, if A equals the zero matrix, it is already in row-echelon form because all its rows are 0 rows. Otherwise, we can find a leftmost non-zero entry, say lambda, in A, and suppose it is in row I. So the matrix looks something like this. The first thing that we do, or the first elementary row operation that we perform, is to swap row 1 and row I. So the lambda is moved to row 1. Then, in order to create a leading 1 in row 1, we multiply row 1 by 1 over lambda. Afterwards, we subtract multiples of row 1 from all the rows below to change all the entries below the leading 1 to 0. Now, we can repeat the above steps for the second row to the last row, and we can continue this process until the last row is a 0 row, or a 0 row except the last entry is 1. Such a matrix is in row-echelon form, and so we have completed the proof.